Section 2.1, Forces and Free Body Diagrams. A force is defined as a push or a pull on an object. When a force is applied to an object, it can start an object into motion, it can slow an object down, it can change the direction of an object's travel, or it can change the shape of an object. Force is measured in newtons. 1 Newton is equivalent to the force required to accelerate a 1 kilogram object at a rate of 1 meter per second squared. There are contact forces. These are forces that act between two objects when they touch each other. For example, an applied force. Non-contact forces are forces that act between two objects without the objects touching. They're also called action at a distance forces. An example of an action at a distance force, or a non-contact force, is gravity. The force of gravity is the force of attraction between all objects due to their mass. The normal force is the force perpendicular to the surface between objects in contact. Whenever an object is resting on a level surface, there is a normal force perpendicular to the surface in which it's resting that acts upward. If an object is resting on a level surface, then the normal force is equal to the force of gravity. Tension is a force exerted by objects that can be stretched. The force of tension in this example is equivalent to the force, the upward force in the cable within this spring. The spring coil is under the same tension. In this example, the force of tension is equal to the force of gravity. Force of friction is a force that opposes the sliding of two surfaces across one another, and it always acts opposite to the motion or attempted motion. There are two types of friction. There is static friction. This is a force that resists attempted motion between two surfaces in contact. Then there is kinetic friction. This is a force exerted on a moving object by a surface in the direction of motion opposite to the motion of the object. Kinetic friction and static friction always oppose the force applied in the direction of attempted motion or in the direction of motion. We have air resistance. This is the force of friction between air particles and the objects in the air around them. We have the force applied, and this is the force due to one object pushing or pulling on another object. A free body diagram is a simple line drawing of an object that shows all the forces acting on an object at one moment in time. Arrows represent the approximate direction and magnitude of each force. A dot in the center represents the object. Let's start with sample problem number 1. You're pushing with a horizontal force to the right against a large printer on a table. The printer remains stationary. Draw a free body diagram of the forces acting on the printer. I will use a dot to represent the printer. We have several forces acting on this object. This object has a force of gravity acting down on it. Since the object is on a level surface, there is a normal force that is exerted by the surface onto the object in the upward direction. Since the object is on a level surface, the force of gravity is equal to the normal force. In this example, you are pushing on the printer to the right with a horizontal force. We will call this a force applied. Excuse me. This object is not moving, even though you are applying a horizontal force. What's opposing this motion? Well, there's a force of static friction opposing the motion of this object. Since you apply a force and the object doesn't move, this implies that the force applied is equal to the force of static friction. In this course, we will be examining objects that are not on level surfaces. We will be examining the forces acting on objects on an inclined plane. Let's look at sample problem number 2. A rope pulls a skier up a hill to the right at a constant velocity. The fact that they mention that this is a constant velocity is an important point when drawing a free body diagram. Draw a system diagram and a free body diagram of the forces acting on the skier. We will use a dot to represent the object, which is the skier. We know that there is a force of tension pulling the object to the right, up the incline. If the object is moving, then there will be a force of friction opposing the motion of the object. This is the force of kinetic friction. If you notice, the force of tension is greater than the force of kinetic friction because the object is moving to the right. Now there is a force of gravity acting down on the object. And since this object is resting on a surface, there must be a normal force that is perpendicular to the surface. So if this is the incline, we'll draw a perpendicular line to the surface, one that touches the surface at 90 degrees. And from that, we will have a normal force. Now, I am not setting the magnitudes equal to each other. We will examine further what the magnitude of this normal force is in further examples. In order to determine the overall motion of the object, it's important to find the net force acting on the object in 2 dimensions. Once you identify all the forces acting on an object, you can calculate the net force on the object, or the sum of all the forces acting on the object. The term net force and the symbol epsilon force are used to represent this sum, but the terms total force and resultant force can also be used. Let's look at sample problem number 1 in determining the net force in 2 dimensions. A baseball player lightly bunts a baseball with an average force of 14 newtons at 29 degrees above the horizontal. The force of gravity on the baseball is 1.4 newtons down. Calculate the net force on the ball at the moment of contact, assuming that air resistance is negligible. For this example, we will use a dot to represent the baseball. And we will draw at an angle of 29 degrees above the horizontal the force that the baseball bat is applying onto the baseball. We know that this has a magnitude of 14.9 newtons. We also know that the force of gravity will be acting downward. The magnitude of 1.4 newtons, and the direction is down. What we want to do is find the net forces in the up and down direction, and the net forces in the left and right direction. Let's examine the force applied and see if we can break it up into x and y component vectors. This force applied has an x component and it also has a y component. When I'm drawing the x and y components, I do not have to put an arrowhead or a bar on top of these symbols, because the subscript y and the subscript x denote that these are directional vectors. The x component is the adjacent with respect to the hypotenuse and the angle 29 degrees. Adjacent hypotenuse is the trigonometric ratio cos. So the x component is equal to 14 newtons cos 29 degrees. If we punch this into our calculator, we end up with 12.2 newtons right. We can calculate the y component. It's the opposite with respect to the hypotenuse and the angle. Opposite hypotenuse forms the trigonometric ratio sine. So the y component is 14 newtons sine 29 degrees. If we punch this into our calculator, we end up with 6.8 newtons up. The force of gravity is in the downward direction, what we are going to do is find the sum of all the vectors acting up and down and add it to the sum of all the vectors acting left and right. So let's find the sum of the vectors in the x direction. In the x direction, we only have one vector. That's the force applied in the x direction, and it is equal to 12.2 newtons right. I'm going to use the color blue since we are referring to the x direction. We'll do the same. Let's find the sum of all the forces acting in the y direction. In this case, we have two vectors acting in the y direction. We have the force of gravity, and we have the force applied in the y direction. The force of gravity is 1.4 newtons down. And the force applied in the y direction is 6.8 newtons up. If we want to add these collinear vectors algebraically, we have to make sure they're in the same direction. I'm going to change this to negative 1.4 newtons up plus 6.8 newtons up. If we simplify this to one decimal place, we end up with 5.4 newtons up. If I want to find the overall net force, or sum of all forces, I'm going to add the sum of all forces in the x direction plus the sum of all forces in the y direction. In order to do so, we will be creating a right-angled triangle. The sum of all forces will be equal to the sum in the x direction plus the sum in the y direction. We know that the sum in the y direction is 5.4 newtons, and the sum in the x direction is 12.2 newtons. To find the overall net force, we can use Pythagorean theorem, and the hypotenuse is equal to the square root of 12.2 squared plus 5.4 squared. If we solve this to two significant digits, we end up with the overall force having a magnitude of 13 newtons. Now we found the magnitude of this force, but we don't know the direction of this force. In order to state the direction, we have to find the angle theta. We will use the opposite and the adjacent to find the value of theta. Opposite and adjacent form the trigonometric ratio tan. So the theta is equal to the inverse tan of opposite 5.4 over adjacent 12.2. If we punch this into our calculator, we end up with 24 degrees. So we found the magnitude and direction of our net force. It's 13 newtons, 24 degrees above the horizontal. Let's take a look at sample problem number 2. A go-kart is being towed north by a car along a road with a net force of 0. This is an important point that we will use to help solve this problem. I'm going to write that down right off the bat. The go-kart is attached to the car by 2 ropes. The tension in the ropes is the same, 31 newtons. The rope makes 22-degree angles to the direction of motion, one to the west side and the other to the east. Determine the force of friction acting on the go-kart. So here we have a free body diagram using a dot to represent the go-kart. We know our direction, north, is up. If we're pulling this car up, then there must be a force of friction acting in the south direction. And our job is to find the force of friction. We have the force of tension, rope 1, which is 31 newtons at an angle of 29 degrees. And we have the tension in rope 2 is 31 newtons to the east, 29 degrees. What I want to do is find the sum of all forces acting in the x direction and the sum of all forces acting in the y direction. I'm going to use blue to represent x and red to represent y. So I know the force of friction is acting south. So the force of friction is a y force. Now the force of tension, I'm going to break it up into x and y components. So for the force of tension rope 1, we have an upward y component we'll call F1y, and we have a westward x component, which I'll call F1x. For rope 2, I have an upward y component vector, F2y, and I have an eastward x component, which I'll call F2x. Instead of using directions, we can use a sign convention. We're going to make north positive. That means that south is negative. And we're going to make east positive. That means that west is negative. So let's look in the x direction. I'm going to list all the forces acting on the object in the x direction. And I'm going to use plus or minus to indicate direction. So I have the x component, which is positive, minus the x component from rope 1, which because it's west, is negative. Now you can see from this diagram, since these are similar triangles, we know that the x component of rope 1 and the x component of rope 2 have the same magnitude, so the net force in the x direction is 0. Now let's take a look at the y direction. I'm going to list all the forces acting on this object in the y direction using plus or minus to indicate direction. We have the force of friction acting south in the y direction, so I'm going to make it negative. And then we have two forces from the two ropes in the upward direction. So we have plus force of friction, force of tension rather, rope 1y, plus force of tension, rope 2y. Now we know that the net force is equal to 0. So that means that the sum of the forces in the y direction must also equal 0. Our job in this question is to find the magnitude of the force of friction. I'm going to rearrange this equation. I'm going to bring the force of friction over the equal sign. When I do, it will become positive. Now let's look at the magnitude of these two forces. For both of these examples, the y component is the adjacent with respect to the hypotenuse and the angle. Adjacent hypotenuse forms the trigonometric ratio cos. So I can replace them with plus 31 cos 29 degrees, and they're both the same. If you compute this in your calculator, you get 12 newtons and 12 newtons. So we know that the force of friction is positive. Actually, I'm not going to say positive. Is 24 newtons. Now remember, it was up here that we determined the direction of the force of friction was negative. So negative means south. So the force of friction is 24 newtons south. Please correct this in your notes. Not sure why that's there. Okay, try the homework problems listed below.